Welcome, ladies and gentlemen. So what I'd like to do is show you how to find all of the zeros when given one complex zero and the polynomial. Now, basically, remember, whenever we're given a zero, we can always use synthetic division to find another factor. So basically, what I'm going to do, the first way I'm going to do this is go ahead and write my zero on the outside and apply synthetic division to see if I can find another factor in the polynomial. So I take my coefficients here. I have 1, -7, and positive 15. All right, so again, with synthetic division here, I'm going to bring down my 1. 1 times 2 plus I is going to give me 2 plus I. Now, adding complex numbers, remember I had to multiply that 1 times both of them, times the 2 and times the I. However, when I'm combining complex numbers, I can only add the reals and the imaginaries. So -1 plus 2, I have 1. I have nothing to combine to I, so I get 1 plus I. Now I have to multiply 1 plus I times 2 plus I. So just going to show my work over here to make sure that I'm doing everything correctly so I can work it out. But once you kind of get used to this, you can start doing this in your head. But just be careful, because that's where a lot of mistakes come in. However, we know since this is a 0, we know my remainder is going to be 0. So you can always double check, know you did something wrong if you don't get a remainder, or if you get a remainder. So by applying FOIL here, I have 2 times 1, which is 2, 2 times I, which is going to be a 2i, I times 1, which is going to be a positive I, and I times I is I squared. But remember, I squared represents -1, so therefore this reduces to 1 plus 3i. So this times this gives me 1 plus 3i. -7 plus 1 is -6 plus 3i. Now I need to multiply the -6 plus 3i times 2 plus i. So I have -6 plus 3i times 2 plus i. Again, applying your FOIL. -6 times 2 is a -12 minus 6i plus 6i. And then 3i times i is going to give me a positive 3i squared. Remember, I squared is -1. -1 times 3 is -3. -3 plus -12 is a -15. Negative I squared plus I squared gives me a 0i, which is 0. So therefore, when I add this, I get a remainder. Now, we obviously know that this is a quotient, but the problem with this being our quotient, to at least to write this as a polynomial, you can see that the coefficients here are going to be complex numbers. That's not really going to be too useful for us. We want to be able to divide this down so we have real coefficients where we could either factor it or use the quadratic formula or continue finding some other zeros that we could, some real zeros that we could use. So the nice thing, though, about having a complex number as your 0 is you know that the complex conjugate also exists as a 0. So therefore, I'm going to use the conjugate. And I'm going to further divide my quotient right here by using synthetic division again. OK, so I bring down the 1. 1 times 2 minus I is going to be a 2 minus I. Here, 2 plus 1 is going to be a 3. I plus -I is going to be 0i. 3 times 2 plus I is going to give me a positive 6 minus 3i. Therefore, those add up to give me 0. So now, if that's my remainder, that's my constant, and that's my linear, meaning the quotient as a factor is x plus 3. Now remember, we can write this as a product of its factors, because remember, this factor times the factor that this 0 produces times the factor that this 0 produces equals our function. And since our function has a power of 3, that means there's 3 zeros, 2 complex, 1 real. So I could write this as a factored form. Now remember, if these are your zeros, to find your factor, all our zeros are the x-intercepts. They're set equal to 0. So the factor would be x minus 2 plus I. Here, the factor would be x minus 2 minus I. So to write this in factored form, I could write this as x minus 2 minus I times x minus 2 plus I. Now, if this problem says to go ahead and find all the solutions, if we were going to go ahead and find the zeros, well, we would just set that equal to 0 and then solve each of these for 0, and by using the zero product property. Well, I can go ahead and write this out. I know my real 0 is -3, and the other zeros are actually listed for us, so I'm just going to list those here. So that would be 2 plus I times 2 minus I. Now, the reason why I wrote them out in the factor form is, one, they might ask you to write them out as linear factors. And the other thing is, there's another way to do this problem without doing any synthetic division. So I wanted to show that to you, just in case you really do not like using synthetic division, or if you're having trouble doing this problem by using like the operations. So if we know that these zeros produce these factors. We know that this factor times that factor gives us our polynomial. Well, again, if 2 and 3 are both factors, and I multiply 2 times 3, that gives me 6. Well, 6 is also a factor. That means the product of x minus 2 minus I and x minus 2 plus I is going to produce another factor that I can divide into my polynomial. So what I'll do here is I'm going to multiply these out. So I have x minus 2 minus I times x minus 2 plus I. Now, if I was going to go ahead and multiply these out, basically what I'd like to do first is to go ahead and group them. Now, you could obviously use distributive property, right? Multiply each of these terms. But to me, that kind of just takes a lot of time. So what I recommend doing is grouping your first two terms. And there you can see that these x minus 2 is similar, and the i's are similar as well. However, the only difference is subtraction and addition. So hopefully you see that I'm multiplying two expressions that are in the form of a minus b times a plus b. And hopefully you remember from factoring and simplifying that that's the difference of two squares. That's going to, when you multiply them, is going to produce a squared minus b squared, meaning your middle terms are going to cancel out. That's very important because rather than having to do all that work on multiplying, I know that that's going to produce x minus 2 squared minus I squared. Well, this x minus 2 squared is a binomial times itself, which hopefully through some practice you'll be able to multiply that out, give you x squared minus 4x plus 4. And then I squared is negative 1 minus negative 1 is plus 1. So therefore, my other factor is x squared minus 4x plus 5. Okay? However, you can notice that this factor is a quadratic factor, whereas if you continually factor this down, or if you factor this down by using the quadratic formula, you would get these two complex zeros. But what's important about knowing that this is a factor, if this is a factor, that means I can divide it into this polynomial to get my other factor. So rather than doing the synthetic division, if you're given a 0, another way you can do this is write your 0 and its conjugate as factors. Multiply them to give you another factor. Then take that factor and divide it into your polynomial to find another factor. So I have x cubed minus x squared minus 7x plus 15. So therefore, x squared goes into x cubed, x times x squared is x cubed. X times negative 4 is a negative 4x squared. X times 5 is going to be a positive 5x. Then I subtract the rows. That gives me 0. Negative x squared minus a negative is going to be a 5x. Or that's going to be minus, so plus a 5x, so that's going to give me a 4x. Minus a negative is going to be plus a, no, I'm sorry, that's going to be a 3x. What am I thinking? 3x. And 3x, negative 7 minus 5 is going to give me a negative 12x. And then you could bring down the 15. 15, you could really do a 0, but we'll worry about that next. X squared goes into 3x squared, a positive 3 times. 3 times x squared is a 3x squared. 3 times negative 4 is a negative 12x. And 3 times 5 is going to be a positive 15. Now, I don't have anything to subtract this 15 from, so I'll bring this one down. Then we go ahead and subtract our rows. And you can see that we have 0, 0, 0. So by using synthetic division, by factoring my factor into this, I get my other factor, which is x plus 3, where we know x plus 3 produces the 0, negative 3. So just two different ways for you guys to look at this when you need to find all of the zeros given one complex 0. Thanks.